Okay, in this section we will discuss that electric field at a point is equal to negative of the potential gradient at that particular point. Now, question arises, what is potential gradient? Gradient is the term applicable whenever a physical quantity varies with respect to separation or distance. Like in the case of temperature gradient, it is written by dt by dx. In the case of velocity gradient, it's dv by dx. Similarly, in the case of potential gradient, variation of potential with respect to distance. That's potential gradient. So SI unit would be potential, it's volt, distance it's meter. So SI unit of potential gradient is volt per meter. So in this particular article, what we need to verify is, we need to prove that electric field at a point is equal to negative of the potential gradient at that point. This is what we are supposed to prove. So nothing new, as was discussed in the previous section while deriving the expression for electric potential difference, electric potential, we will proceed in the same manner, right? So let's consider one-dimensional case. It will be much simpler. Suppose this is positive source charge and this is positive x direction. Let's consider P and Q are the 2 points which are very close to each other. If the distance of point P from the origin is considered to be r, then it can be considered to be r minus dr. So this distance becomes dr. It's a very small distance. It's a very small distance between point P and point P. They are vanishingly closer towards each other, right? Now this is positive charge. Due to positive charge, the potential will be positive. Due to negative charge, the potential will be negative. And potential due to a point charge varies inversely as the distance. So due to the positive charge, here the potential will be larger, here the potential will be slightly smaller. So if the potential at point P is considered to be V, then at point Q, which is closer than point P by distance dr, the potential will be given by V plus dV. This is a positive charge. So as the point comes closer towards the observation point, the value of potential will keep on increasing because potential due to a point charge varies with the distance like this, right? So by definition, potential difference between these 2 points, P and Q, P initial point, Q final point, it will be VQ minus VP. It is equal to work done per unit charge in moving that charge from P to Q. Now since this distance is very small, small amount of work done will be required in moving charge Q0 from P to Q without any acceleration. This is supposed charge Q0, right? So this charge is to move from P to Q. Now what is the potential at point Q? It is V plus dV. What is the potential at point P? It is V. So if we evaluate it, V minus V get cancelled, we will be left with dV is equal to dW divided by Q0. You can put this as equation number 1. Fine. So I've simply made use of the basic definition of the potential difference. Now further, let's find out the work done. As I told you earlier, if this charge is left free, this being positive source charge, it will experience a force along the direction of the electric field, so it will be Q0E. Now this charge is to be moved from P to Q against this force. I mean, without any net force acting on it. So a force is to be applied in a direction opposite to that of this force, so that it can be moved without any acceleration. So the force that is to be applied, it should be Q0E in a direction opposite to that of the electric field, right? So small work done. It's given by scalar product of force and displacement. Suppose P to Q. The direction of displacement is like this. Let's consider it by dl. So F vector dot dl vector. Now look, F vector. This is the electrostatic force which this charge Q0 is experiencing under the influence of charge capital Q, right? Net force acting on charge Q0 should be 0. So in order to compensate this force, we need to apply force in the opposite direction out of the same magnitude. So the force which needs to be applied is minus Q0. Minus signifies the very fact that the force applied must be in a direction opposite to that of this electric field. Dot dl. So further, minus q naught. It's the scalar product of electric field and this displacement, small displacement vector. So scalar product is magnitude of E, magnitude of dl, and cosine of the angle between these two. Now look, due to this positive source charge, electric field is directed along this direction, along the positive x direction, and dl is directed towards the origin. So what's the angle between these two? Electric field along the positive x direction, dl displacement, that is from P to Q along this direction. So angle is 180 degree. Cos 180 degree is minus 1. So minus q naught E dl minus 1. So that will give us q naught E dl. Now look, the magnitude of PQ, either you can consider it to be dr or dl. So magnitude wise, dl definitely is equal to dr. But the increasing direction of r is along the positive x direction, while the displacement of this charge when it is moved from P to Q is towards the origin. That is in vector form, dl vector, it should be equal to minus dr vector. Or rather, you can write it like this only, dl is equal to minus dr. It simply represents both are of equal magnitude, and this negative sign signifies that both are measured in the different direction. The increasing direction of r is towards the positive x axis, the displacement dl is towards the origin, opposite direction. So if you substitute the value of dl over here, what you get is dw is equal to q naught E minus dr. Right? Put this as equation 2. Now simply substitute this value of dw over here. What you get is, from 1 and 2, we get dv is equal to, in place of dw you can write minus q naught E dr divided by q naught. Q naught get cancelled, which implies that dv is equal to minus E dr, which further implies that E is equal to minus dv by dr. This is the mathematical verification of this very, very important relationship. So, the conclusion is, electric field at a point is numerically equal to the negative of the potential gradient at that particular point. So we will try to discuss some special cases, and also we will discuss the significance of this negative sign. One more thing, I told you in the previous section, electric field, it can have two SI units. One is force per unit charge, that is Newton per coulomb, and another SI unit can be dV by dr, that is volt per meter. So SI unit of electric field, or in SI the electric field can be represented either by Newton per coulomb or volt per meter. So SI unit of electric field is either Newton per coulomb. Electric field is force per unit charge, or volt per meter. Anyway, let's concentrate on the significance of this negative sign. Look, let's take some example. This is a positive source charge. Electric field is directed along this direction, right? Electric field always emanates from the positive charge. While if there is a negative source charge, electric field will be terminating, or it ends at the negative charge. This is the direction of the electric field. Now consider these 2 points, point A and point B. Due to positive charge, the potential at a point must be positive. Due to negative charge, the potential must be negative. Due to negative charge, potential will be negative, like minus 3 volt, minus 2 volt, minus 8 volt. That is due to negative charge. Due to positive charge, the potential will be positive, like plus 2 volt, plus 4 volt, plus 6 volt, and so on. Now also due to a point charge, we know potential is inversely proportional to the distance of the observation point from the source charge. Now over here what happens is, in magnitude, potential will be greater at those points which are much closer to the source charge in magnitude. So if I say here VA and VB, it will be positive. So VA would be greater than VB, or VA minus VB is positive. So in this direction potential is increasing, or rather in this direction potential is decreasing. This is the direction of increase of potential. So this is the direction of increase of potential. Increasing potential. So you can well observe the direction of the electric field is opposite to which the value of potential increases. The value of potential increases along this direction. The electric field is in the opposite direction. Or in other words, this is increasing potential direction, so this is the decreasing potential direction. So in other words, the electric field is always directed along the direction in which the value of potential decreases. So negative sign suggests that the direction of the electric field is opposite to which the value of potential increases, or along the direction in which the value of potential decreases. Right? Here also you can justify it. Here VA in magnitude would be greater than VB. Suppose it is minus 3 volt, it is minus 2 volt. Obviously negative potential. Obviously minus 2 volt is greater than minus 3 volt. Therefore in this case VB is greater than VA, or VB minus VA is positive, or VA minus VB is negative. In this case, this is the direction of increasing potential. It is the direction of increasing potential. So again, you can justify the fact which we have discussed for the positive source charge. This is the direction of the electric field. I have taken here a negative source charge. So electric field always terminates at the negative charge, right? So this is the direction of the electric field, and this is the direction in which the value of potential increases. So again, it justifies the fact that the direction of the electric field is opposite. This is the increasing potential. It is opposite to which the value of potential increases. I repeat, the negative sign in this expression signifies the fact that the electric field, its direction is opposite to which the value of potential increases, or the direction of electric field is always along the direction in which the value of potential decreases. So this is a very, very important concept. We will discuss some other important case as well. So, in case, I've explained earlier, the electric field inside a conductor is always zero. The electric field inside a conductor is always zero. There are certain regions where that region can be shielded from the influence of external electric field. So that we'll discuss in the later section in the topic electrostatic shielding. But here, in the region where electric field is zero, the value of potential would be constant. Why? Because if E is 0 in any region, suppose net electric field is 0, then dV by dr is 0. Differentiation of constant is 0, right? Therefore, V is constant. So this is again a very, very important result. So in a region where the electric field is 0, the value of potential in that region must be constant. I'll give a simple illustration over here. Suppose there is a uniformly charged spherical shell. It's a uniformly charged spherical shell. Say, charge Q is uniformly distributed over here, right? And suppose its radius is R. We can consider any point. This is A, this is B, this is C, and let us consider this point to be D. Points A, B, they are inside the uniformly charged spherical shell, while point C lies on its surface, point A is lying outside. So inside the uniformly charged spherical shell, the electric field is 0. We'll discuss again in the later section. So if the electric field is 0, as per this, the potential must be constant. So the potential at point A would be equal to the potential at point B, which would be equal to the value of potential at any point on its surface, and it should be equal to constant. Right? So in a region where the electric field is 0, the potential at that any point, including any point on its surface, is constant. While we will discuss later on, at a point outside, this uniformly charged spherical shell will behave as a point charge, which can be imagined as all the charge is concentrated at the center. So in that case, the formula for the potential at point D would be K capital Q divided by this distance, the distance of point D from the center. Right? So this was an important illustration.